0 at this point. Again, notice right where it reverses course, right here, the slope of this curve, which means the derivative of this curve, is 0 at this point, and that's why the second derivative goes through 0 at that point. So you can use that. Now, let's learn from this. Okay, let's learn from this. What you can learn is if the second derivative is greater than 0, then what does that imply? Then the original function y is, and I'm going to explain this term in a minute, concave upward. Okay, and I'm going to give you an example of that. It looks like this. This is what concave upward means. It's just something that goes up like this. This is concave. If you think about concave, it just means something that's curved like this, like a parabola, and it's facing upward. So the open area here is facing upward. So it holds water is another way that the book sometimes explains it. It holds water. So if it rains on the sky, then water fills it up. That's concave upward. Okay. Now, how do we know this is true? When the second derivative, which is this function here, is greater than 0, so from this region here all the way over, everywhere up here, the second derivative is greater than 0. And let's follow this up to the first graph. Looky here. It's concave upward. So look, if we follow this up to here, then from here over, it's concave upward. Now, why does this work? It's not quite so important for you to be able to work your problem why, but if you want to know why, the reason is, what we're evaluating here is we're looking at the slope of this graph here. This is the slope, which is the first derivative, and this is the slope of the first derivative itself. So what this graph is predicting is how fast is this slope actually changing. And so in the end, when you back it out, what it's actually predicting is this guy, is it curved kind of like this, or is it curved kind of like this? Because look here, in both of these cases, like up here, you're going to learn in a second, this is concave downward, right? But in this case, on this side of the hump, and also on this side of the hump, in both cases, the slope is actually negative, okay? But in one case, the slope is changing in a way that defines the fact that it's concave downward. In the other case, it's changing in a way that defines that it's concave upward. That may or may not be clear to you. I think the main thing to look at is the example here, which is really showing you that in this region, the second derivative is positive, and so because of that, it's concave upward. The other thing that you can learn from this is that when the second derivative is less than 0, the original function y is concave downward. And an example of that is when it looks like this, okay, concave downward. Okay? And that makes sense because everywhere this function was negative, if you kind of follow it up here, which would be from here over to here, it's concave downward. So that makes sense. Okay? And then the natural question you're going to have is, well, what happens if the second derivative is exactly equal to 0? Look at here, it's right at this point, kind of like right in there. And that is the division between concave upward and concave downward. So when the curve kind of does a little S like that, and it kind of begins to bend over and go the other way, that's called an inflection point. Okay? So this is a new word. Inflection point. And so you can kind of just think of that as a reflection or an inflection is when the thing starts to kind of turn over. Okay? So these are the properties that you're going to be able to use to basically sketch lots of different graphs. So let's go ahead and do that now. I'm going to erase this. These properties are the ones that are really important for you to be able to do the problems. And I hope that this example is kind of giving you a basic background into how to remember these. Okay? So the problem is, on a test or something like that, here you have f of x equals x cubed plus, it's x cubed minus x. And the problem is, graph this, okay? Well, even though I told you that you can get a much more accurate sketch by finding the x-axis crossings. I'm going to not do that, and you're going to see why. It's sort of an optional thing. You don't always have to do that. The first thing that I like to do, okay, is find where these local maxima and local minima occur. Okay, that's going to be really important. So the way we do that is we take the derivative, okay, so over here I'm going to take the first derivative. The first derivative is equal to, actually what I'm going to do, just for space, is I'm going to do it right underneath here. The first derivative is what? From this it should be 3x squared minus 1. And I think you should be able to do that because we've done these problems before. Now, we're not going to use it just yet, but the second derivative, I'm going to go ahead and take it right here so we have them all together. We're going to use it later. What is the second derivative, which will be the derivative of this, which is 6x. So we're going to have all our function and our derivative in one place. Now, let's find out where there's a local maxima or a local minima. So what I need to do is I need to set the derivative equal to 0. So if I take 3x squared minus 1 and set it equal to 0, which is the derivative here, I'm setting it equal to 0. Let's solve for this. 3x squared is equal to 1. Just move the 1 over. And so then x squared is equal to 1/3, right? So then x is equal to plus or minus the square root of 1/3. Okay? And when you put this in a calculator, you'll find this is roughly plus or minus 0.6. Okay? 0.6. So those are the x values, the values along the x-axis where we have an inflection point. Okay? I'm sorry, not an inflection point. The x values of where we have a local maxima or local minima, which remember is where you have basically any hump or valley like this. But what this is saying is that this would be at 0.6 and this would be at negative 0.6. I have no idea if the graph looks like this, but I know that I have a local maxima or local minima at these points. But that doesn't really help me so much because that tells me the x value, but I have no idea what the y value is, so I can't really plot anything yet. So how do I plot it, or how do I figure it out? Well, I know the x value. I'm going to take this x value, I'm going to stick it into f of x, and I'm going to get the y value. So let's do that. F of 0.6, I'm just plugging in 0.6 into f of x, and I'm going to let you crank through that on your calculator on your own, and you will see that that equals negative 0.384. Okay, that's just a number that comes out. And then when you put negative, when you put negative 0.6, f of negative 0.6, what you will get is a positive 0.384. Now, we're definitely not done yet, but we have enough to get started plotting this thing. So down here at the bottom, I'm going to have a little graph kind of in the corner here. Something like this. So this is x and this is y. This is the graph of f of x, which is what we're trying to sketch in the first place. What we have shown here is this is going to be positive 1, this is going to be negative 1. Up here, this is going to be positive 1, and down here, it's going to be negative 1. Okay? So what we have said is that at x is equal to 0.6, which is just a little bit past half, and negative 0.384. Okay? So roughly right around there, at that point, we have either a local maxima or a local minimum. Because what this tells me that I have a local maximum and local minimum at 0.6, comma, negative 0.384, and also at negative 0.6, comma, positive 0.384. Okay, that's what this information tells me here. So I have another one at negative 0.6, which again is just a little bit past half, and positive 0.384. So I have something there. So pretty much from that information right there, if you know, I mean, I guess it could come down like this, and then it would bend over and come down again, but in order for it to bend down, it would have to have another local maximum there. really there's only one way that you can fit this to have a local maxima here and a local minima here. So the graph is going to end up doing something like this. But in order to prove that, just to put the nail in the coffin, we're going to do a couple more things. Okay, let's find out where there's an inflection point. Let's figure out where y, second derivative of y, is equal to 0. This is the second derivative, so at 6x is equal to 0, I just set this equal to 0. So at x is equal to 0, I know I have an inflection point. And so then I want to find the y value, so f of 0 is, when I plug it into here, I can see right away I'm going to have 0 here and a 0 here is going to be a 0. So at the point 0, 0, I have an inflection point. Which means what? It means that the curve kind of bends over and starts to go the other way. So I submit to you that from this information you have enough to sketch this curve, and so you can prove to yourself that it kind of goes up to a local maximum, bends over like this, and it kind of goes up like that. And that's a sketch, okay? These x values aren't perfect. You know, they're not symmetrical or anything like that. But you know you have a local maxima here, you know you have a local minimum here, and the kicker is that you have this inflection point where it starts to change course, and so you know that this is the only shape of the curve. Now to get accurate values of where the curve crosses the x-axis, you could set your function equal to 0 and you could solve for those. I'm not going to do that here in this problem, but you could do so. Now if you just wanted to have a triple check to make sure that you were correct, okay, let's look at the second derivative evaluated here at this point. So the second derivative, which is this, evaluated right here where we have this local minima, which would be at 0.6, x is equal to 0.6, what is this equal to? This is equal to 0.6 times 6, right, because that's what I'm plugging in here, is positive 3.6. So what we have shown is that at this point, where this minima here occurs, the second derivative is a positive number. Since the second derivative is a positive number, it's greater than 0, and that tells us that y, the original function, is concave upward. And that proves that we have our graph exactly right, it's concave upward. If you were to put negative 0.6 in here, over here at this point, and evaluate it, you'll get a negative number, and that'll prove to you that it's concave downward, which is exactly what we wanted to prove.